Okay, let's begin the class. What's your idea on the role of KD? Reduces oscillatory. Other answer? Reduce overshoot. Other answer? Reduce shortening response time may not be correct. I don't think it is correct. Yep.
Increasing stability of the system.
Increasing the stability of the system. You mean increasing stability is by pushing more the closed loop poles to the left, or what? What do you mean by that? PI system is stable already, right? Other idea? What?
It will change the steady state.
Huh?
It will change the steady state.
Yeah, but that's not the role, of course. Have you tried out the system with PID? Not yet. You can simulate, or you can calculate, or just you are imagining the role, is it?
Well, it is not.
No, PI already has zero steady state error, so no need derivative to do that. Okay, let us begin with a simulation first. Yeah, because you don't have time, I take the role of simulating the system. Okay, you are very busy, right? I have proportional here, integral, and then I have the derivative over there. Do you realize what is the format of the derivative control over there? Is it KDS or what is that? So I have the KD times N and divided by S plus N. And N is a number that I can adjust. Do you know why we have to apply this? In theory we can do this. Theory, yeah. When you are creating your block diagram. However, when you apply this into a real system, it will not work. It cannot work. Okay? It cannot be realized. And the same thing when you apply this into Simulink will not accept that. It is not a physical system. Okay, not a physical system, and then you can see this transfer function is not proper. For it to be proper, you need the order on the denominator to be at least the same as the order of the numerator. Yeah. So let us see if S is equal to 0, what happened with the
KD.
It's just KD, right? Huh? If S is 0, S means the frequency. Yeah. If your system works with a constant error, the error is a constant, which is unlikely. Yeah.
Zero.
Huh?
Zero.
Sorry, 0. Yeah. 0 over 0. It's not a 0 over n, so it's 0. Yeah. So there is nothing happen. So that means when the frequency is 0 or you have constant error, the derivative control will not do anything to you. Okay, and then when S is small, what happened with this? S is small, non-zero but small. If S is small compared to N, then this will be approximated by Ns over N. Yeah. So yeah, this is KD times S. So this is perfectly the derivative control that we want. Okay, what happened when S is very large?
Yes. Yes.
KD. When S is large, so this will be approximated by KD and S over S. So this is KD times N. Okay. When N is very, very large, this system becomes proportional. Okay. So adjusting the value of N is crucial. Yeah, it is crucial. N. And because S can vary from 0 to some finite number. It depends on how your system responds. N is a constant of the system. So when you want to apply derivative control, you have to apply this. Yeah. All right. So let us do the simulation, which I have already in here. Yeah. So if you want to try, you can choose this to be applied to Kp, Ki, and Kd, and also N. Yeah. And then the mass is 1000, C is 10. You can try that later at home if you have time. And then the difference that I have from here is that I am plotting the control action. Okay. The good thing from simulating is that I can take out the signal from proportional control, integral control, and then derivative control. Okay. This one should be derivative. And then I compare them in a scope. Yeah, you get what I mean? Okay. And then in here, I also plot the error. So I want to see how does the control action responds to the error. Yeah. The gain, because the error is very small, I cannot see it compared to the control action. If I multiply by 100, then I can see how it is compared to the control action. Yeah, but it doesn't change the dynamics. No, it is just for plotting purposes. Just to see if error is this much, what will be the control action. Okay. So what do you see here is that the black one is the proportional control action, the blue one is the integral, and then the red one is the derivative. Okay, the dotted, this is dash, dash green line is the error. Proportional control tries to follow the error proportionally, as you can see. Yeah, when the error is large, it's large, and then when it is small, small, and then when error is 0, control action from proportional is 0. Okay. And then what happened with the integral? Integral goes slowly. Yeah. The reaction from the integral control is slow, and then after that it becomes a constant, non-zero. Why is that? Anyone know? The error by this time is 0 already, right? But the integral control is still there. Why? You see again what happened? Or this one? At the steady state, the desired velocity is achieved already, but the integral control action is still there, non-zero. Why is that so? Anyone know? Huh? Sorry? No. Not because of that. Logically, what you can see from this system?
The C is S.
No. Do you remember what this system about? This is a car, speed control of car, yeah? With wind disturbance, okay. The disturbance is still there, yeah? So what do you think the integral control doing it there? Yeah, it is cancelling the disturbance. Yeah.
Why is it only the integral that?
Yeah, good question. The first thing is that proportional control, it's a good question. So proportional control action, it only multiply with the error, yeah. Okay, when the error is 0, then the control action will be 0, right? Yeah. So which is why the proportional control action when the error is 0, it is 0. Okay. What about the derivative? The derivative do is that it will do this dE over dt, yeah, like this. So when the error becomes 0, constant, the derivative of a constant is 0. So control action from derivative is also 0. Yeah. Meanwhile, if it is integral, then what you are doing is actually you integrate the control, the error. Yeah. When you do integration of the error, this value will not become 0. So it will still be there. Yeah. And that is exactly needed to counter the disturbance. Okay. And yeah.
So it's taking account of this language.
Yes.
So it means that the PI will run the derivative will not original and the derivative doesn't take the disturbance into account. So it will be
Yeah, it when you only apply proportional and derivative control, it cannot handle the disturbance. The one that cancel out the disturbance is the integral control. Yeah, you see in our derivation last Monday, yeah, when we derive the steady state value, I think we have here. Yeah. Okay, this one. Yeah, the one that is canceling out is the integral. You see, ki over ki, it is 1, yeah. And also we have 0 over ki in here. What about the derivative? The derivative part, it has s square on the top. Yeah. And in here, there is no derivative part that's going to cancel out the fw. So the integral part, that's the one that's canceling out. Okay.
so what is the role of the D?
Yeah, the role of the D is actually when you have sudden change of error, then the D is useful. Yeah, when you have a large change of error. So let's say only in the beginning that the integral, the derivative part helps to speed up your control action, but after that it doesn't do much. Yeah, only 5 seconds. The first 5 seconds, the derivative part, the derivative control action work. Yeah, because the derivative error is large. Yeah, the rate of changes in the error is very large in the very beginning. Yeah, after that it doesn't really help. Okay, if you let's say going mad or not patient, let's say I want my derivative control action to be very large, and then you enlarge this, you make it, let's say 2000 or 5000 compared to 160 and 7. Okay, 20 times of the current derivative control action. What will happen is in here is that, what do you see? It very, very small, so your response will be very, very slow. Yeah, and in fact, if you try to simulate this, you can see that, yeah, when the derivative constant is very large, it reaches the steady state much longer compared to this setting. No, overshoot is small. Smaller. Overshoot is smaller, but then you reach the steady state longer. Yeah. So be very careful when you are using the D part. Yeah. PI control is mostly usable for most cases. Yeah.
So is one sudden change in error.
Yes, yes, correct. Sudden change in error. Okay, which I summarize in here. Where is it? Oh, do I have here? No, I don't have. Wait, yeah, I want to show you the result when I have this. Okay, so you see, and then you can do interesting thing by having several step input into the system. Okay, so if I run this, let's see over here, yeah, what I do exactly. Okay, where is it? It goes to the left. Okay, so what I'm doing in there is that I set the initial desired velocity to be 1, and then after that I change to be -1, means I go backwards then. Okay, I'm going backwards, and then after that I go forward again, and then this is the response. The black line is the response. And you see what happened with the control action is this. Yeah, this is what happened with the control action. Okay, as you can see, the integral control is still very slow, and then the derivative part helps when there is a big changes in the desired value. When you change your desired value, then the error changes. Yeah, so the derivative part is working over there. Derivative part is the red one. Where is the legend? Legend is not there. The red part is the derivative. The green one is the error.
So it helps faster, not the response.
Yes, yes.
It helps to go down the error.
Yes,
When
yeah.
when the change happens.
Yes, when the change happens. Okay. So if let's say you have your desired value is a ramp, compared to the step you have a ramp like this. If this is your desired value like this, yeah, then a derivative control is not really helping. Okay, because the derivative in the error, if you have this kind of desired value, it's not large. Okay, compared to having a step input like this. Yeah? Okay, sudden change. Yes. Okay, is that a question? Oh, okay. Any other question before we move to the next part? Yeah.
So ideally, we want all graphs.
No, the green one is the error. Green is the error, right?
Like what is like velocity is much. What is like to reflect the real movement?
Oh, these are all the control action. There is no output there. The ideal, you are saying ideal response, yeah. The ideal response would be like this. No overshoot for the velocity. This is velocity. Yeah. This is the ideal case.
So this case is gonna be down, right?
These are all the control action, not the response. Yeah. If it is the response, then I have to show other graph. Wait. So the response is here. Okay, this is the response, yeah, the black one. This is not ideal, of course, not ideal because it still has overshoot. Okay, I don't have time to mingle with the PID to make the overshoot to be 0. Yeah, you should have more time than me actually. Okay, so if you have time, you can adjust it. Yeah.
So like blue one is like our input, right?
Yeah, the blue one is our input.
Like
Correct.
ideally we want it to follow the blue line, so like we'll follow
Yeah.
what we say. Right?
But perfectly following the blue one is impossible. So just like this, like.
And then in the previous graph,
Yep.
it shows like the ways how the system tries to make it higher.
Yeah, with that. So the three graph that you see, these are the control action. The control action from the derivative, the integral, and the proportional. We see it one by one. Yeah, we compare them.
Say that I remove like the integral part.
Yeah.
Will it, does it affect the
Yes, it will affect. If you remove the integral part, then the steady state error will not be 0. So you cannot reach the desired value. Cannot. There will be still error. Yes, of course, it changed.
So what we're looking at in the proportional integral and derivative is the output of this control system into the plan.
Yeah, it's the control signal to the plant. Control action with the control signal to the plant, yeah. But the graph just now is the individual
Response of the system.
individual control action. Yeah, the black one is from the proportional control action, the red one is from the derivative, and then the blue one is from the integral.
And tadi yang input dan outputnya itu dari combine tiga-tiganya.
Yes, of course.
So like it becomes more accurate when you have three of them, right?
Accurate? No.
Is it possible like to just use
Not possible. At least proportional integral. We discussed already when we are computing the steady state value, yeah, on Monday, that when you are using PI control, you can reach your desired value. PI control, yeah. Steady state error will be 0. Your question, what's your question again?
I was like wondering like whether we need three of them. Is it possible
Not in all situations we need the 3. Usually PI control sufficient. Okay, the D part you need when your input is like a sudden change of the input. If your input is very slow, okay, listen to me, yeah. If your input is very slow like this, if this is your input, then you don't need derivative control. Okay. No, yeah, to help you to counter the sudden change in the error. Okay. Yeah.
still possible without
You're just from the toilet, right? Okay. Come on. Just checking.
I want to ask.
Yeah.
So it's still possible for the system to exist without it.
Yes, of course.
But there is not as
No, it can be as fast. As I said, when your input is like this, then the derivative part is very, very small. So you can remove it. Yeah. That's why it depends, right? If the input is step, then PI control can work. But then if you compare with PID, then the D part will help you to fasten out your response in the beginning of the response.
But it's optional.
It is optional. Okay. All right. Anything else?
It's basically based on
Yeah. Based on your reference. Yeah. If you have oscillating input or randomly changes input, then derivative control will help a lot. Yeah. And sometimes when that's the case, you don't need the integral control. You You just need PD control. Okay. Yeah, PD control. The I part, the integral part, you need it when you expect your system to have a steady state value. You need that. Okay. If the input changes like this, random changes input, integral control is not needed. Yeah, it's no use. The integral control will have no use. Why is that so? Because the response is very, very slow. Yeah, you see here. Where is the graph again? Here, yeah. You see, the integral control response very, very slow in here, yeah. Can you imagine if the input goes like this? Well, integral control will not be able to catch up with this kind of changes. Cannot. So in this kind of case, you use PD control only. Yeah.
So we can say that integral control forces our system when it comes with the
Steady state value.
Forces the is it useless or
It will make your response slower, correct? The integral control will slows down your response. Yeah, it waits.
Slows down the response, but it ensures the steady state.
Yes, ensure steady state value achievement. Okay. In this kind of case, you don't want accuracy. You just want fast response. Okay. Chris, still have a lot of questions.
Not really important, see, but like, what are the cases where you don't want to have a steady state value?
If it is like this, if your response changes a lot like this.
Like,
Chris, stand up. Stand up. Come here. Come here. Sit down. Okay, come here. Sit down. It's this kind of situation. Yeah, you don't want the integral control.
so like for cars, you don't want integral control.
For cars, for cruise control, for car, you need integral control because normally your desired value will be like this. Okay, it's a step input for your desired value. Let's say you set it to be 60 km per hour. Okay, you don't want when you are cruising. Okay, now 60, now 59, 65, 70. You don't want it like that, right? Or you want it like that? Of course. Yeah, which is why for cruise control, PI control is a must. Yeah. Unless yeah, for a worst situation, which is very rare, you want your car to follow the speed of the lead car, and then the lead car changes the speed. You apply PID here, and in here they apply on off. You know what's on off?
gas.
Yes, you press the pedal gas and release. Press, release. Oh my god. Yeah, I've been in that kind of car, and it's not nice. Okay. So you can analyze the closed loop poles. What do you think the closed loop poles comparison? For PI and PID. If it is PI, this is the one that we discussed yesterday. Yeah? Open loop poles 0 and minus C over M. You remember minus C over M is very close to the origin. Yeah? And then you have the minus Ki over Kp over here. Yeah. Yeah.
Oh yeah. Banyak zeros ya. Oh, bisa. Oh iya. Oh, man.
Yeah, this is like this. Sorry. Yeah, you are correct. This is the X, yeah. Sorry. This is X and this is the 0, yeah. Yeah, I was wondering, we should have the 2 closed loop poles, right? So why we have only 1? So the situation will be like this. So I'll use red color, and then one of them will come here, one of them will come to the left. Okay, what about the PID control? Where is it? Like this. Open loop pole still there. Open loop pole, sorry, X again. And then this open loop 0, we have 2, yeah. Instead of 1, we have 2. So let's say the open loop 0 are a real number, okay, over them numerator. So they are here. What do you think will happen? What will happen is this. It's over here, over there, then it just go like this, yeah. One to the right, one to the left. Yeah, the limit are the zeros. Yep. Yeah.
So we make that close loop transfer function.
Yeah. Ki over kp, so you want ki to be large, you move to the left. Yeah. So that's the situation. Okay, let's move on to the next topic. If we have the Ks to be this one, what would be the closed loop transfer function? What would be the closed loop transfer function? Let's do the math.
Over B1S plus B times 2 times M over MS.
Like this, right?
Yeah, MS plus A1.
Is it like this?
I think number is also.
No, I think
The top one is
one is
times
also 1x.
Oh, the same?
Same, yeah.
Oh, okay. So this one,
B1 plus M.
so what's the result?
Open the bracket.
Yeah, open the bracket. How to open the bracket? Do we need opener?
Yes.
Buy Tokopedia? Tokopedia. S square.
B S square B1 M. No, B1 M1, sir.
B1 times B1 plus M1 lah.
B1 M1.
Oh, B1M ya. B1M only, okay. What about the S? S
S
B1C.
B1C.
B1C plus B2M.
plus A1, yeah.
Plus A1.
And then the constant will be
PD
Plus
plus A2. Okay. So how do we adjust the value of B1, B2, and A2 here in A1? In this case, what do you do? If you want to adjust this, then the first thing you do is that you set your desired pole location. Where is your pole location? Let's say you want your closed loop to be here, -5 and then -10, let's say. Okay, and so you need to match it with s plus 5 and then s plus 10, which is s squared plus 50, not 50, 15. No, I say 50 plus 15s. No. But not nice, right? So we have 15s and then so you just match the form. Yeah. What else? B2M plus A1 is 15. There you go. You have how many variables? 4. And then how many equation? 3. Then this is a linear equation, right? Using algebra. You remember chapter 7 and 8? Chapter 7 lah. Chapter 7 engineering analysis. So you have
Oh.
Hah?
Yeah.
You have A1, A2, B1, B2. Okay, this is 1, 15, and 50. 4. Okay, we have 4, yeah. And we have 3 here. Okay. The first one is just B1, yeah. And this is M.
M.
And then this is C times B1.
C and B1.
B2. A1 is 1. Okay. And then in here 0, 1, 0, C. Okay, you can do it. Right? How many solution that we have? Is it infinite solution or no solution at all? Yeah, you review again. It can be no solution, right? Yeah. What is the requirement so that you have a solution in here? Huh? What's the requirement for you to have a solution?
We need to address one.
No. M and C is known.
Oh.
Yeah, the 1, 15, and 50, it has to be in the range space of this matrix. Okay, range space. Okay. So I have taught this, and then it can be released in exam. Obligation, right? Yeah.
What are the advantage that we approach the system through the post but not through the real observation?
Real observation. Okay. When you are doing this, then you have initial guess of your controller parameters. Okay. And after that, you try out in your system, in your real system. Of course, your model, we are modeling it with 1 over ms plus c, right? Maybe the c is different, maybe m is different, so the response may be different also. But at least from here, you have a initial guess, and then you fine tune your system after you do this, rather than you trial and error control parameter, right? So that's the advantage.
Are there any rules that we can directly use as the overall error propagation?
The first one is that you need to know what kind of desired input that you have. Is it a step function? Is it ramp? Is it sinusoid? And then after that, you can design the system type of your system. We will discuss later what is system type. And then after that, you design your pole location, because the response of your system is defined by the pole location, right? If let's say you want your system to be overdamped, then your poles has to be distinct. If you want your system to respond fast but small overshoot is okay, then you might place it at a complex number. So that will affect how you choose this B1, B2, A1, and A2. Okay, it will change this number, right? Yeah. Do you know why the denominator here, it is called the characteristic equation? This is called the characteristic equation. Anyone know why?
The denominator.
The denominator of the closed loop transfer function, yeah, this one, yeah, or finally this one. It is a polynomial, but this is also called as the characteristic equation. Okay, do you know what's the reason?
Like all the parameters.
No. It defines all something. It defines the characteristic of the system. Yes, the whole behavior of the system is defined by this. Yes, which is why it is called characteristic. Okay, and this is determined by the plant transfer function and also the controller transfer function. Okay, which is why you need to adjust the controller transfer function so that the characteristic equation is the one that you need or the one that you want. Yeah, it's like when you go to the canteen B1 canteen, yeah, not this B1, yeah, level B1 canteen. When you go there, you need to set already what I want to eat, right?
Yeah.
Correct. Today on my lunch, I want to have fried rice, let's say. You are not going there and then you scrolling around and you don't find anything that you want. You can do that for your lunch, but not for the control system. No. From the beginning, you need to know what you want for your system. First, you know what you want, and after that, you know what you are doing. Okay? Is this make sense to you? Yeah. So you collect all of the requirements of your system. Yes.
You have to find
Desired characteristic first. Yes. And after that, you design the controller to match the desired characteristic. Pretty much like doing engineering component design. You set the Sigley's method, right? What's the first method? Defining the needs, right? Yes. Identification of needs. Yes. So the problem definition is that you have to set the desired characteristics. So these are all related process.
The approach by setting the poles with by setting omega and
The same. Because you are setting omega and zeta, you know what will be the overshoot, what will be the settling time, right?
we are just translating and zeta to the
Correct. Yeah. Yes. Which make it very easy, right? Yeah, you know already, it's easy, right? So I don't think we have time for this exercise today. although I want to do the exercise, so I will give this as the homework for next week. No. We will just do this. Root locus I will extend to next week again. Yeah. So we'll do this.
The other one?
Huh?
The other one and the other one.
Yeah, both are.
Yeah, both are delayed again. Okay. It's okay. I go easy on you lah. The next problem is this, which I will give to you. Do you know how to determine this? Yeah, the undamped natural frequency is just the omega n, yeah. And then damping coefficient is the zeta, and then percentage of overshoot. But the resulting system is this second order or third order? Third order. So you need to use the what? Yeah, you have to see the dominant poles and then the extra pole. Okay, are they close to each other or are they far away? If they close to each other, then you cannot use the MP, which is e to the power of minus sigma times pi. I think sigma over pi. You check again the formula. What about the last part? Steady state error? Huh? You can use either final value theorem or you can through the Bode form. Okay. No need to simplify. Just finding out the steady state error. Compute using FPT. FVT, final value theorem, or you can use the system type. System type we haven't discussed yet. System type. Okay. Now this is the third question for your homework. Yeah. What do you think will be the answer? What do you think the answer is? Or say anything that you can answer on this question. How far you know lah?
We'll find the damping ratio.
Okay, what's the damping ratio?
I don't know it conversation.
You want to track unit step input, the output must not exceed 1. Okay, so it should be under damped, critical damped, or it should be over damped.
Under that.
Input is 1, yeah. Step input, unit step.
Sure.
The input is unit step. Under damped will be like this. Critically damped, no overshoot. No overshoot. So at least your zeta is 1. Okay, you know from that your zeta is at least 1. It can be 2, 3, 4, or 1.01. Okay, what else we can find out from the problem? Yeah. Not yet, we haven't discussed the same setup. So you can only answer the damping ratio, yeah? Because you know what's the damping ratio, where you will have your closed loop poles. Is it here or on the real axis? It will be on the real axis, that's correct. Tadi.
Under that system have imaginary part and real part for a ROV complex state. Typically, them and them only has it on real axis.
Yeah, okay. Remember that, yeah? Yeah. No. Critically damped, 2 value but the same value.
Oh yeah.
Okay. 2 value but the same value. Okay. So let's say if if your system is like this, root locus is like this is root locus, where you want to place your closed loop pole? Is it here? For this case, is it here?
On the
Real axis, right?
Yeah.
So it can only be here, yeah. Over here is too slow, yeah. So it can only be over here. If it is here, then it is critically damped. If it is there, then it is over damped. But along this line is okay. Okay. So you just need to prove that you have that how many open loop poles? You have 1 over s squared plus s, and then you will have something in here. Okay. Open loop poles. What is the open loop poles in this case? Negative 1 and 0. How many 0?
None. Zeros, right?
no, two zeros.
No. The pole location. Where's the pole location on this? 0 and minus 1?
Take up the S.
Oh, where's the other one? 0, yeah. So we have 2 0 and then 1 in minus 1, right?
1 0
1 0 1 1.
becomes s plus 1, sir.
Okay. Right. What am I thinking? Okay. Yeah, this is s 1 plus s, yeah. So 0 and minus 1. Okay. So from the plant you have this, and then how do you place your controllers pole and 0? It will affect the system's situation. Okay, it will affect the system situation.
There is no 0. Zeros.
Yeah, no 0. So let's say you have your controller to be s plus a, this is s plus b, let's say like this, yeah. You place your a over here, then your b over there. Sorry, b is like this, yeah. B like this. So what will happen is that this is what will happen. Sorry, under color. It will be like this, and it will be like this, and then goes there.
Like I said, goes there.
Yeah, later we will learn. Yeah, this is the asymptote of your root locus. No, we have 2 asymptotes. Sorry, 2 asymptote. Then it goes up. Sorry, not go here, but it goes up. It should go up. Yeah, it should go up. Okay, this will be the non-dominant pole. Over here is your dominant pole. Okay, so if you place your pole over here and over here, then you can satisfy the zeta greater than 1. We have only 2 asymptotes. Then one goes up and one goes down, and that's just the situation.
Left one doesn't consider.
No, this is not an asymptote.
No, I mean, you don't consider the root locus of the left.
Yeah, we have 3 poles. In this case, if this is your resulting system, then we have 3 closed loop poles.
Yeah.
We have 3, yeah. So one is coming from here, and the other 2 is coming from here. Yeah. So you cannot answer this yet. No. It's not complete. I think after root locus, then I will give you this. Okay. 15 more minutes. Let us take a break 1 minute and then we'll continue with this while you are thinking on how to answer that. Okay, let's begin again. Okay, let's continue. What do you think? How to answer this? No. How? What is the range of K so that the closed loop system is to be stable?
You don't show that question.
I forget. I have to click the second one. Yeah. Yeah, make closed loop transfer function first, and then after that, both must be negative, and then you find out the requirement on K. Okay. Okay. Now we will learn about Routh-Hurwitz criterion, which will make the procedure to find a K to be more systematic. Okay. The first one is that you express the denominator of the closed loop transfer function like this. Okay, like this one. Express the denominator of the closed loop transfer function. And you have to realize that this is a polynomial in S. Okay, S squared, S power of 1, S power of 0. Polynomial, yeah. And then the second step is that we create a table, a Routh-Hurwitz table from that polynomial. The third step is that we use the criterion. Okay, the criterion will only give you a number of how many poles or how many roots of that polynomial is on the right half plane. It will tell you that, but it will not give you the roots. Okay, it will not give you the roots. It will only give you how many roots are on the right half plane. And this is the table of Routh Hurwitz. So you have your denominator of the closed loop transfer function like this. Okay, let's say you have s to the power of n. N can be 100, can be 100, yeah, can be 1000. And then after that, you create this table. The first column in here is just you label them with the power in s. Okay, starting from the highest power until the lowest power. The lowest power is 0, yeah. And then the A0, A2, A4, A1, A3, A5, these are the constants. Constant multiplied by the s in there. Okay, so let's say if you have a polynomial like this, s power of 3 plus 8, okay, then you create the table. So what we can fill up is that this will be the variable here, yeah, 1, and then after that 7, and then after that nothing, so 0, yeah. And then s square we have 5, and then 8. Okay, 0 is not used, apparently it's not used. Okay, so this is the first variable that you have. Okay, and then you need to compute what is b1, b2 there, and then the c1, c2. Okay, well, what is b1 here? You using that
5.
b1 is 5 times 7 minus 1 times 8, yeah. 5, 7 minus 1 times 8 over 5. So it's 35 minus 8, which is
5.4.
what? 5.4. I trust you lah. I don't want to compute. And then after that, the b2 over here, it should be 5 times something in here minus 1 times something in here, but this is all 0, yeah. So b2 is 0. Yeah, this is 0. And then you continue with the c1. c1 is b1 a3, so you get b1 to here, and then this to here, divided by that. Yeah. So the result is that b1 times 7 minus 1 times 0 divided by b1, which is 7. Okay, so finally you have and this is 7. Okay, this will be your first column. Yeah, that first column. So what to do with that first column? You check how many sign changes in that first column. Okay, sign changes is positive, negative. We don't care about the value. Okay? We only care whether it is positive or negative. In this case, this is positive, 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 positive. So no sign changes. Yeah, no sign changes mean there is no roots on the right half plane. There is no sign changes, so there is no roots on the right half plane. No.
For the each one.
For the what?
For the bagian naman kiri. For the each one.
No. Okay. Let's make it clear.
This is all the rows or only one row?
Only the first column, not row, column.
And yes, okay. The first column.
Yeah, only the first column. The second column you don't care.
So the first column.
Okay, only the first column, yeah.
So no sign changes, then
If there is no sign changes, then
poles are on the left.
no sign changes.
Poles are
Roots are on left half plane.
Pole left.
The roots of this.
Poles.
What if this is the numerator? It's not always the poles, okay?
It's just a method. So
This is just a method to check the polynomial, yeah?
it can be used both in zeros and
Of course, yeah. Remember, yeah, this is the way we check the polynomial, not the poles. But we can use this method to check how many poles are on the right half plane.
we cannot determine the value.
We cannot determine the value. Okay. Another example, which is the first example that we have. So this is the closed loop transfer function. If I want to know range of k which make the system stable, then I will check the denominator, yeah, not the numerator. Okay. Yeah, so this is the polynomial. Because I want to know what k that can make the system to be stable. Okay, so this is the reference, and that's my polynomial. Okay, that's the Routh table. 1 plus k, 5 minus 3k. Do I need to compute b1 and c1 in here? No, yeah, that's the only thing that we have. Don't force yourself to compute s minus 1. If this is the situation, there is no s minus 1, yeah? Yeah, if you want it to be stable, then we don't want sign change. I can say stability. Why? Because I am checking the denominator of my closed loop transfer function. Okay. So for the first element, 1 plus k positive. Because k is positive, yeah? So the first element must be positive. And then the second element, how to make it positive? Yeah, the k must be less than 5/3. So the final result for k is that k must be between 0 and 5/3. Yes.
Is it valid if we use the criterion of 1 plus k less than 0, 5 minus 3 less than 0?
It is valid, but the k will be negative.
Is still okay.
Not okay.
not okay for first number.
What can be real number?
No, it is real number, but your k negative is not. It's not going to give you a good response.
So we will always use criterion more than 0.
No, the k over there is positive. Okay. Let's say k is negative. Then what will happen with your system is that if you give it, let's say, Sobri, you come here. Sobri, you come here. Sobri will just go to your side. Yeah, it goes the other way around. It is stable, but it goes the other way around. Okay. Okay, yeah. Yeah.
We can use the method in exam, right?
We can. You can. If you only want to check stability, you can choose this method. Okay. Other example about this one. Can you work on it?
Yes.
Yeah, now you work. Okay, don't just sit down. Try something. Okay, maybe 2 or 3 more minutes, then we are done. Yeah. Write down what was your answer. Okay, the first one to get it correct will get bonus point. Only the first one, yeah. No second one. Yeah, for a group.
Yes, over 1 plus yes times yes.
square plus
Simplified.
Finish? Anyone?
How to find the range?
Yeah.
Something over this harus dari komunitas.
Oh yeah, of course, table ya. You need the table ya. Okay.
That's only give us the sign.
This one. Okay ya.
It will just give us if it's
One.
Oh, you mean I think you mean this one because
no.
this one. Routh.
You understand? Itu udah gue kasih value-nya itu kayak denominator.
That's closed loop, right? Closed loop, sir.
Yeah.
That's it.
Find this
Okay.
function.
No. Find. Yeah, the K stability.
Oh, find the key.
Yeah, K for stability lah.
H.
Yeah, using RH.
A1 is
Using RH. Find K for stability. If it is closed loop, I did already here.
Oh my god.
I did it already.
Oh my god.
Come on.
You don't be doing bro. That.
yeah.
What?
Yeah.
What? Denominator ya. Yeah, denominator.
No, we B1.
S power of 3 will be 1. And then this one. S power of 2 will be 2 plus 5. And then 60. Okay.
To be simplified, bro.
Huh?
No need to simplify.
Why simplify?
Never mind.
You have to simplify, right? We need to get.
No, for like B1 or C1.
No need.
Itu zero. Zero berarti ini zero. Zero itu zero.
We'll take over the one.
Bener-bener menunya tapi kamu juga sekarang gua nggak bisa
Party square.
Berapa selesai lagi?
Wait.
Two is equivalent to
sekali bro.
Yeah.
We have one change.
One change. No, you don't want change.
Oh, you don't want change.
Yeah, what is the value of k so that there is no sign change, right?
Oh, zero ya. Okay, now I mean to make this not negative. So we need to start the game plus C1 is C1 then zero, right?
basically you want
Correct or not?
because
A3 is
1 row 1
Use that. Kita boleh do.
61 34 right?
yeah.
Oh yeah.
Type A square.
Oh 60 bro.
Pero ito 61
Which one?
B1.
B1 61.
61. Back from beginning again, man. Wait.
We have
Yes.
Find out the k so that the system is stable. So there is no sign change. Yes.
They got me, man.
Wow, it takes so long for you.
3 zeros. I'm probably one right here.
My brain,
Man, so we can process on this.
Yeah, we can.
Hey.
Who's faster?
This is wrong already. Ya, mau that one langsung ya.
Mine might be wrong also, right? I don't know.
Bro, you can check your wrong.
Not yet.
There has to be no S.
Nah, you follow that.
Video ini harus S.
One. Why is it 6? Where is 6k? No 6k.
6KS. Ulang.
I think that's
Five
right.
K biar dia stable. Biar
Huh?
Nggak tahu.
What is your B1?
B1
Yeah,
Ah,
Discontinue our
what's your B1?
I should that. If I can calculate it.
For the S0,
Yeah, from C1 you only get that K to be positive from C1.
Yeah.
Any positive K will do.
Hey man, this game, bro.
First column.
Okay. Let's stop here. I think it will take too long. What's your answer?
A is bigger than 0.
Yeah. That's reasonable.
Oh, nice.
Okay. What?
K is in the range of 0 to 2.5.
No.
Also, you got Anthony. This will be bigger than 0.
Okay, let's see this. Yeah. You check again. I think this is correct. Yeah, I think this is correct. So when we derive this, we have that B1 equal to this, and this is the C1. Okay. We want the first column to be positive in this case, yeah, because K must be positive in that case. You see, what's K to make this positive?
0.
At least 0, right? Yeah. What about this? To make K to be positive, sorry, this to be positive, K must be greater than 0. It cannot be 0, yeah. It has to be greater than 0. Also over here, greater than 0. So to make positive, any K greater than 0 will do. Okay. So you don't have to find out the smallest K which is negative, no need.
Karena misalnya is smaller than 0,
Yeah.
can be 1.
Correct.
No. You said 0 to minus 2.5. Bigger than 0. Cannot. Okay, yeah. I think you get your B1 correct, but you take the wrong conclusion.
Yeah, I think we're all.
Yeah.
Okay.
Yeah. So Haikal and Ansel group is correct, yeah. But you follow my
I follow you. Because
half then half. Okay, take it again. I have one more example, which is work already, and this is for you to study. Yeah, you can study this. So the homework next week will be those two exercises. Exercise number 1, the drone control, hover drone control. The mass is unknown. Okay, and then the second one is about the finding the omega n, damping ratio, and etc. I'll see you again on next Monday.
So the homework is